Good morning. Hi, everyone. I hope you're doing
Professor.
okay, so this is my share. Last week, we ended on looking at one of the demos where someone was sitting on a stool holding a bicycle wheel that was spinning. By flipping the wheel upside down, and the person and the stool start spinning the other way. So this is similar questions, but we want to be able to answer not just in which way the person will start spinning, but will we be able to also figure out the magnitude of the angular momentum of the person and the stool together. So in this case, the person and the stool are one part, they're together. All right, so let's see if we can answer this question. So we're treating person, stool, and the wheel, those three objects all together as our system. You can see there is no external torque acting on the system, right? Nobody is spinning these three different things. And there's no external torque, which means the angular momentum of the system should remain constant, should be conserved. So think about what happens before the person flipped the wheel and what happens after the person flipped the wheel. Okay, I'm going to go ahead and start our votes. You can take a moment to think about this if you need, and we will have a discussion afterwards. Okay, so right, let's take another 10 seconds if you haven't voted already. All right, let's take a look at this together. I'm gonna go ahead and end the poll. All right, so we have a majority voting for LW, which is the same magnitude as the angular momentum the wheel had before you flip it. Okay. All right, let's see how, if we set up the equations, how will the equation tell us? Let's take a look. I'm going to say I'm using conservation of angular momentum. So this is the physics you're trying to use. And that tells me when there is no external torque, my momentum initial is equal to the momentum final. So let's just say we are saying the wheel is originally spinning with the angular momentum pointing upward. and we will just call that to be our positive directions. So our initial momentum consists of the initial momentum of the wheel and the initial momentum of the person plus the stool is equal to final. There are two parts, final momentum of the wheel. Now, all of these are still vectors, so I'm going to put a little vector sign on them. And the final momentum of the person plus the stool. This is what we're trying to find, right? And let's look at each of the term one by one. What is the initial momentum of the wheel? The wheel originally is spinning with an angular momentum LW, and we said we just call that to be positive. So I'm going to say this is L of the wheel. What is the initial momentum of the person plus stool? What do you think?
The person and the stool?
Yes.
So initially, it's 0.
The 0. Very good. Okay, very good. All right, so thank you for all that also responding in chat. It is 0 because it simply just sits there holding the wheel. The wheel is spinning, the person was not. Okay, and the final momentum, angular momentum of the wheel, when you flip it upside down becomes, what does that become?
When you flip it upside down, it becomes negative LW.
Yes, very good. Thank you, Juan and Sally. And this is what we're trying to figure out. So L person and the stool, final, we wanted to find out. And we don't know what this is. So take a look at this equation. What does the L person has to be? L person plus stool is going to be
2LW.
2LW, very good, 2LW. So that the total momentum of the system is simply LW upward. Okay, so if you flip one of them to be upside down, the person has to be 2LW so that these two add up to be still LW. Okay, so that's C. Now, if you answered LW, you were thinking if the person was holding the wheel and neither the wheel or the person were spinning, nobody is spinning. So 0 angular momentum to begin with. And if you start spinning the wheel yourself and give it a LW upward, and then yourself will spin the other way around, negative LW in the other clockwise direction. Okay, so that's when you're holding a wheel that was not spinning at first. But if you already were holding a wheel that was spinning, so someone else must have already made the wheel spin and hand it over to you. And then you flip it, and then you're going to pick up 2LW. So that's a little subtlety here. Well, we need to just, when we come up with, when we came across these type of questions, always start with, okay, I'm using this physics and start from the fundamentals and break it down into, okay, what are the different momentum terms for different objects that's in the system? And that way it's much harder to make mistakes. So, all right, so let's look at another question, also has to do with the conservation of angular momentum. We have a bug that is sitting on a rotating disc. Again, we are assuming no friction because so that we can say the external torque is 0, which means the angular momentum is a constant. Okay, so that is the condition for using conservation angular momentum in this format. Now the bug starts to crawl toward the center of the disk. As the bug moves inward, the magnitude of the angular momentum of the system, what is that? What do you think that is? This should be fairly quick. So I'm gonna go ahead and open the poll for you. Don't jump to conclusions. It's asking for angular momentum. It's not asking for velocities. Okay. Okay, so how about 10 more seconds? Let's wrap up. 10 more seconds. All right, any last minute vote? Okay, I'm gonna go ahead and end this. We'll take a look. We are exactly tied between B and C. This is that it decreases, C that it remains constant. All right, what is it asking us? It's asking about angular momentum. And what had we just talked about the angular momentum of the system? This is asking for the system, not even just part of the system, right? The angular momentum of the system remains what?
Constant.
Remains constant. That's what we are trying to do this whole time is when you don't have external torque, the angular momentum of the system, initial equals final, which means L simply is just a constant. It does not change. That's why initial and final are equal. It doesn't change, right? So simply it remains constant. So be a little bit careful when reading questions. It's asking for angular momentum.
Professor, could you go back to the first question we did really quick, please?
This one?
Yes, thank you. Okay, I got a picture. Thank you.
All right, so okay, so what if I asked you the magnitude of the angular velocity?
Wouldn't it increase?
Yeah, would that increase? What do you think? What the rest of you think?
I think it would because of like the figure skater example, since our moment of inertia is decreasing because we're getting our masses all coming closer together. Since L remains constant, the angular velocity has to increase.
Very good. So this is just like the figure skate example, or bring your dumbbell closer to your body. So by having the buck crawling toward the center is like some part of your mass is now closer to the center, reducing the total rotational inertia. And as a result of that, increasing your omega angular velocity, because I times omega is angular momentum and I times omega is a constant. So if one of them decrease, the other one has to increase. So if I had asked you angular velocity, you would answer it increases. It increases. Very good. What if I asked you a different question that is related to the velocity, but not exactly the velocity? What if I had asked you, what about the kinetic energy of the system? Okay, the buck and the platform. So we know that the kinetic energy for rotation, I will remind you what that is defined to be 1/2. So translation is 1/2 mv squared. So when you have trouble memorizing the formula, think about, okay, how are we going to change the linear case to the rotation case? So m becomes I and V becomes omega. So kinetic energy for rotation is 1/2 I omega squared. So how does that change? All right. So this one, let's do a little bit brief discussion in our breakout rooms. And once you're done, take a minute or two, and then we will have a discussion and come back. I will visit room 4, I believe, is what should I be rotating to today. Hello, everyone. Hi, Brendan, Carlos, Jacob, and Jonathan. What do you think about the kinetic energy of the system? Does it increase or decrease? Or does that remain constant?
I'm not too confident with my answer, but the way I'm thinking about it is similar to the ice skater.
Okay.
In that when you, like, if they brought their arms closer, they spin a lot faster, and I think that would increase the kinetic energy.
I agree with you. Omega does increase. So let's see. Kinetic energy depend on omega. In this case, omega increase. But kinetic energy also depend on I. In this case, my I decreased. So what do you do when you have two factors? One is decreasing, one is increasing.
I'm not sure.
Wouldn't it just remain the same?
Yeah, would it remain the same? So that all depends on, well, one of them decrease, one of them increase. How much does one increase and how much does the other one decrease, right? So that will factor in. So you might wonder, well, give me some numbers and I could calculate it. But we also, let's take a look. We notice that, well, how much omega increase, and where does the omega increase coming from? It's coming from I omega remains a constant because I omega is L, okay? So that tells you just how much omega increased. So you can see that we just do a little bit trick by writing our I omega in square into I omega times omega. This is omega squared. You know that, well, I omega is our angular momentum, and that is constant. So that part doesn't change. You can see that, well, the effect of I increase and omega decrease, that is all taken care of. Now, and you have another omega, so that when this omega increase overall, kinetic energy will increase. So the original intuition you had is correct, that the kinetic energy of the system does increase. Okay, so now we can see it more rigorously by breaking down I omega squared to I omega together as a constant, and you have another omega. Does that make sense?
Yes, thank you.
Thank you. All right, I'll see you all shortly in the main session. All right, so let's go for another 10 seconds and then we'll wrap up. Okay, any last minute vote? Okay, I'll go ahead and stop this. We'll take a look together. All right, so this is our results from majority voted for increasing the kinetic energy. The rest voted for decreasing. All right, so any thoughts anybody would like to share with us? How do we parse out the kinetic energy? We know that omega increase. We also talked about I, rotational inertia decrease. So one is increasing, one is decreasing, and they both is going to matter. So how do we parse that out?
So with my group, what we kind of talked about was that total kinetic energy is rotational plus translational. So in the beginning example, it's only rotational kinetic energy, like at the beginning. But once it starts moving, it has translational kinetic energy and it has the rotational energy. So for once the bug starts moving, it has that extra translational component, but also the moment of inertia is getting smaller. So angular velocity is increasing, but it's larger, but it's also the component that's squared. So they both should proportionally be the same amount smaller, but the one that's bigger is getting squared. So that's why I think that overall both the rotational and translational energy of once the bug starts moving should be greater. So that just means that overall it should be greater.
Okay, so I hear two different thoughts. The first thought was the bug was crawling, so there are some kinetic energy moving associated with the motion inward. Let's just assume that the bug moves very slowly, because you can't always do that. You can just move very slowly just simply by changing your position. So we don't worry about the translational kinetic energy, and that's very small. We're only comparing the rotational kinetic energy before and after. And you also talked about the rotational kinetic energy. The second thought you guys had was that the omega is squared. Do you think that square make any difference?
Yeah, because it'll make it, for a little small change, it'll just make it an even, bigger one.
Yes, very good. So I is decreasing and omega is increasing. So you might wonder, oh, just how much I affect K and how much omega affect K, Ke, right? So you might wonder, okay, omega is to the power of square. So maybe the increase in omega makes a little bit more difference in the kinetic energy. So to be able to reason that more rigorously, let's write I omega squared into I times omega times omega. And what is I times omega? I'm gonna group I and one of the omega together. What is that?
It was L.
That is L, right? And what does L do during the whole process?
Remains constant.
Remains a constant, very good. So you can see that way you're be able to parse out this complicated one increase, one decrease by grouping one of them, two of them together. So this remain constant, leaving one more omega, and that is increasing. You can see, okay, so that's a constant, another variable increasing the overall kinetic energy increase. So A is indeed correct. Very good. And you might wonder, wait a minute, didn't we say energy can just come out of nowhere? So in this case, they can increase kinetic energy of the system. Where does that come from?
The bug crawling.
Okay, coming from the bug. So the bug is doing exercise. The bug is burning its energy, its lunch, its chemical energy inside. Yes, so that part of the energy is coming from the bug. Very good. All right, excellent. Let's take a quick look at this one from your pre-lecture or bridge questions. It has to do with two rotating discs. You're dropping one of them onto another. So one of them is rotating, the other one wasn't. the difference between two cases, you're dropping one of them onto a another equal mass, and then the second case, you're dropping them onto a two times of the mass. After you drop it, the entire disk will start rotating together. So now it's asking, in which case the final kinetic energy of the system being the biggest. So you can see here, we are going to take advantage of that same approach. Is kinetic energy in case 1 is 1/2 I omega squared, okay, I1 omega 1 squared. But we're going to write I omega squared into I omega omega. So I omega together is the angular momentum. So simply angular momentum times omega 1 squared. Knowing that the initial angular momentum between these two cases are the same because it's involving the same disk rotating with the same velocity. So they have the same L to begin with, right? Is just whatever L this disk has. The other disk was not moving, so that doesn't matter. So they all have the same L. So I'm not going to differentiate which it is. So case 1 has 1/2 L omega 1. Case 2 has 1/2 same L omega 2. So the question becomes, comparing the kinetic energy has become comparing the omega between these two after you drop it. So, which means after you drop it in case 1 and after you drop it in case 2, which one moves faster? Which one overall rotate faster? What do you think? With
In
omega
case
1?
1.
In case 1, and why is it case 1 faster?
It had the same initial rotational velocity, but
Okay.
now case 1 has just 2m for total mass instead of 3m. So it's the same initial velocity trying to rotate something that's lighter.
Very good, very good. They all had L to begin with. For case 1, they had 2 of the disks together. So if you want to write I for the 2 disks, is simply 1/2 times mr squared. In this case, is 2mr squared is the total rotational inertia times omega 1. But case 2 is the same, but is now being dropped onto twice of the mass. So the total mass is bigger. Omega 2 is going to be smaller. Very good. So as a consequence of that, case 1 will have more kinetic energy. So you can see that is sort of a strategy we do when we try to analyze kinetic energy is by relating it to the angular momentum because that is a constant. So we only need to worry about the part that is changing, that's the omega. Okay, so let's look at another question here. Comparing of different shapes. Previously, we had looked at both of the shapes are a disk. Let's look at different shapes. We have a hollow sphere, and we already know how to do an I for a hollow sphere. That's among the list of the rotation inertia. Usually, the question will always provide it to you. Has a mass m and radius 1.35 meters. It is also rotating with this angular velocity. Now this mass is now being compressed into a solid sphere. Now it just deforms, it changes the shape while it's rotating. Never mind how it's done, but it is done. And it become a different shape, which is like this, with no external torque being applied. So you can think of, well, maybe there is an external force to compress it, but you can apply force in such a way it does not generate any torque, so that our angular momentum conservation equation is still satisfied. Okay, so that's what's trying to tell you. Now, what can you say about the final angular velocity of the new shape? All right. Okay, so let's do a vote here. I don't think this one requires a discussion. All right, so let's go for another 10 seconds. Please wrap up your vote. Okay, I'm going to end this right now. Right, it looks like we have a majority of you had agreement on the angular velocity increase after you change the shape of the hollow sphere. Okay, so being with the equations listed, this should be easy to compare because originally is 2/3 mr squared, but later on it become 2/5 mr squared, right? So overall this had decreased. So omega will increase, very good. So C is correct. But I hope that eventually after doing a few of these different questions, when you look at this, you can group the similar questions in your head, thinking, oh, this is nothing different from what I saw about ice skater bring her arms closer, right? Bring some of the masses closer to the center. This is also no difference from the bug crawling closer to the center. Because changing the shape in this case from a hollow sphere to a solid sphere is simply by bringing some of the masses toward the center, closer to the center, not exactly at the center. So overall, you are decreasing the rotation inertia and increasing the angular velocity. So even if you were not given these equation, let's say you don't really have these in front of you, you should still be able to have that qualitative reasoning and you can still answer the question correctly. Okay, so really this is not anything new. It's still the same type of question, which is a very classic type of questions for conservation of angular momentum. You'll see that a lot. We'll now look at more a concrete example where we have to do calculations, not just to predict qualitatively. Okay, so a person on a disk. Well, this is not different than a bug on the disk, right? You can change this person to a bug, but the sort of the process will still be the same. Now we do have some numbers to work with. We have a person, the mass is given, stands on a spinning platform, and R and mass of the disk was given, and initial velocity of the disk was given. But the person now changed its position. You can see bring part of the mass closer, or it could simply be by person was originally toward the center, but now walking further, right? So it's the same type of problem. Now the person moves 2/3 of the way toward the center of the disk. That is the final angular velocity of the disk. So this is what we're trying to calculate. We'll do this together. Okay, so now this system has two parts. Okay, so now let's say, well, I know our physics is conservation of angular momentum. Which takes on this particular format when we don't have external torque, right? So it doesn't really say anything. If it doesn't say anything about there is friction, which means it doesn't, if it doesn't explicitly say there is a friction, we can assume there's no friction to generate that external torque, so your momentum remain constant. So this is the physics we are going to use. Our system, of course, is the rotating platform, the disc-shaped platform, plus the person. One of them is can be treated as a rigid body, the disc. So you need to use 1/2 mr squared to calculate the I, rotation inertia for the disc. The person, we are not going to treat it as a rigid body because the person simply just changing the positions. As far as we're concerned, we can treat the person as a point. Because all points of the person in terms of the status of the motion is the same, right? You're just a 1 point rotating. So I, for the person, you will just use mr squared for the person. Okay, so you treat these two differently. One is a rigid body. The other is a point particle, a point for the person. Now let's plug in this into, apply it into conservation of angular momentum. Okay, so we said L initial is equal to L final. My L initial has two parts. One is the disk, one is the person, and they're rotating together with omega, right? So omega I. Okay. Finally, I still have I of the disk, but it's the final. So you can do a subscript saying a final here, or if you think, okay, my subscript getting really long, I'm just gonna add a prime on it. So it's a little shorter to write, that's also okay. So I'm gonna leave that option up to you, whichever, however notation you wanna use, that's up to you, as long as you're consistent. So you can put a final little notation on all of them. Okay. So what is I initial of the disk? It's 1/2 mr squared, right? So it's going to be 1/2 mass of the platform, mass of the disk, times radius of the disk, r. So both of these are given quantities, but I'm not going to plug in numbers yet. I want to see what I can cancel before I plug in numbers. The person is the mass of the person, and P times r squared. R is where the person is at. So initially the person is at the edge, right? So you're going to use the distance of this point particle to the center, which is also r. So I'm going to say MP r squared for the person. These two added together is the total rotational inertia for the system. And it has a certain omega to begin with. Okay, so now let's look at what happens after the person walks closer. Well, that doesn't change anything about the disk. So I prime is still the same as before. So you can simply just put 1/2 mr squared again for the disk. What is now changed is the person. The person now walks 2/3 of the way forward. So it's eventually here, right? Person was standing here. So walks 2/3 of the way in. So the new distance of the person from the person to the center is going to be what?
0.63 meters.
Yes, which is also given. So you can use call it a D or a little r or something to represent that. But at this point, I want to eventually be able to cancel some of the variables. And I see I have an r all here. So I'm still going to use my r to represent that. I'm just going to call it 1/3 of the r because it walks 2/3 of the way in. So which means it is going to be at 1/3 of the radius away at the end. So here it becomes a mass of the person, and 1/3 of the radius squared becomes 1/9 r squared omega final. All right, so I'm now ready to calculate my omega final is equal to this whole thing divided by this. So 1/2 mdr squared plus mpr squared divided by 1/2 mdr squared plus mp 1/9 r squared omega I. I do this simply just because I want to cancel the ones I don't need and cancel my r squared. Okay, so which makes sense. Omega f should depend on omega I, simply depend on how mass are now distributed. It shouldn't really depend on your radius, right? Because the only thing that's been changing is how your mass is now being redistributed. So omega final is equal to 1/2 md plus mp, the person, divided by 1/2 md plus 1/9 mp, the person, omega I. Now at this point, feel free to plug in the numbers of the different mass that were given to us in kilograms. and you can get your answer. So this is 1/9 of the 72 kilograms times 1.4 radians per second. So I got a larger rotational kinetic angular velocity later on. Okay, so I can calculate exactly how much that is. Okay, so but if of course you are more than welcome to plug in these numbers at the very beginning and get a specific number for your total I and a specific number for your total I final. It will still give you the same result, but perhaps the process is just a little bit more complicated because you have a lot of numbers to manipulate. And that's also easier to introduce a mistake in the middle. So you probably have already been very familiar with this approach that we always wait until the end to plug in numbers. We cancel what we can and do this at the end. Okay, so you can see this is one type of very classic example where you have a rotating platform and you change the mass distribution by bringing part of the mass in or bring part of the mass outward. And now you know how to calculate it. Okay. All right, now let's look at another example that you have already seen this in your pre-lecture, but I wanted to go over this. This is slightly different where the person who's not already on the platform, in this case, the person is running and it jumps onto a merry-go-round, jumps onto a rotating disc. And after the person had landed on the disc, they rotate together. Okay, so there's a request to go back to the slides. I'll stop here for a moment.
Could you scroll up a little bit, please? Sorry.
Okay, up.
Yeah, I didn't get the. Okay, thank you. Sorry about that.
No problem. Okay, so what happens, this is also another type of classical problem, is it has to do with a sort of a linear motion to begin with. You can see that the person was originally has a translational motion, it wasn't a rotation. And then jumping onto the disc and they start rotating, right? How do you calculate the overall angular velocity after the person has landed? So the approach is still the same, is you're treating the person and the platform as one entire system. L remains constant, right? We know how to calculate L after is really the person and the disk added together. Okay, depending on where exactly the person has landed, is right at the edge is simply mr squared. But if they had running sort of in the middle, halfway in the middle, you have to use the corresponding distance. That part we already know, I omega. The one thing that is slightly different is the angular momentum calculation before is different. So before the disk was not rotating, the angular momentum is brought by the person. It's running. And recall, we say, well, for that kind of angular momentum, we do R cross P to calculate it. Okay, so when it's not a rigid body, a point particle, we do R cross P. So you can see that relative to the rotational axis right here, my R is radius R, right? My P is the momentum is mass times velocity and V, and they are perpendicular, right? This is perpendicular. So that's the cross product becomes, they multiply together because sine of the angle is 90 degrees, simply 1. So L before is simply MVR, and you equate that to I omega, you can find your omega afterwards. So this is a slightly different scenario where you have to consider MVR for angular momentum initial. So you can imagine a various different change to the scenario, but it still remains the same problem. You can see, okay, I have a bullet that being shot into either a disc or could be a long bar. And after the bullet is embedded in it, it starts rotating. You see that is nothing different from this problem. All you need to treat it as conservation of angular momentum, right? You do MVR for the initial angular momentum of the system. So if you have a bullet, just do that for the bullet. If you have a person jumping, do that for the person. And you can even combine these two problems together. You can say, okay, after the person jump onto the merry-go-round, they will walk toward the center, halfway toward the center, or 1/3 of the way, or whatever distance they walk toward the center. Calculate the new rotational angular velocity of the system. So you can even combine these two type of problems together. And again, they are all the same type of question, right? All right. Okay, so we're pretty much out of time. I do want to have a little bit more discussion on this topic, but also sort of a review of all the different conservation laws we had previously using a problem, a ball rotating, rolling down a hill problem, and we're going to use different perspectives to solve the same problem, sort of as a recap of everything we have done so far. So we will do that on Wednesday. At first, do a wrap up, and then on Wednesday, we will start the new topic of static equilibrium. Is where we balance a rigid body. You want all the forces and all the torques to be balanced. So we will do that on Wednesday as well. Okay, so that's all for today. I will see you guys next time. Have a good rest of your week, everyone.
Bye, Professor. Thank you. Have a good day.
Bye-bye. Thank you.